Hello everyone and welcome to this new episode of our tutorial series on Salome-Meca. In today's video, we're diving into setting up a nonlinear static analysis in Codaster that involves contact conditions. We'll be using the AsterStudy graphical interface to walk through the process step by step. And let's go with the default stable version of Codaster that is available. The AsterStudy interface lets us build a command file for Codaster. The workflow here covers all key steps: meshing, model definition, materials, boundary conditions, solving, and post-processing. A second way to quickly get started with Codaster is by using the assistant, which is what we are going to see here. Right-click on Current Study, add Stage with Assistant, and then select Contact Analysis. As the Contact Analysis wizard opens, the first thing it asks for is the mesh you'll be working with. Next is the model definition, as we are working with 3D elements. Then comes the material definition before getting to the boundary conditions setup. And we're going to use the predefined groups in order to enforce degrees of freedom. Now the pressure is going to be applied on the body, press, and hot press groups. Next thing is going to be the contact definition. We are going to select the master zone here and then the slave zone. So that actually finishes the job of the wizard. Now we're able to see the generated commands on the construction panel to the left. So at this point, the whole model is actually assigned 3D elements, which is not suitable for the studs since they are supposed to be 1D beams. So I'm going to double click on the AFE model command, then I'll pick the correct groups for the studs, and finally I'll assign them beam elements instead. And with that in mind, since we're representing these studs with beams, I'll need to define their geometric characteristics. That's done using the AFE-LM command, which I'll add in here. Once I open that up, you'll see a panel where we can define the beam's cross-section by making it circular and setting its radius. And now I will select the different studs groups to which this section will be applied. Now when it comes to the geometric properties, since we're dealing with hollow cylinders, we need to specify both the radius and the thickness. Now instead of directly entering the radius and thickness, we'll create a variable on the fly. That way the code will show the variable name, which will help us later when we do a design of experiments and vary these values easily. Alright, so now let's move on to the mechanical properties using the diffie command. Instead of entering values directly, we'll create variables on the fly for the Young's modulus, the Poisson's ratio, and also the density. Once we've done that for the valve, we'll just copy the same approach to define the material for the stud, adding stud suffix to those variables. At this point, I'll also rename the output variable from diffie so that it is easy to identify it specifically as the material for the stud. Once we have defined our materials, we'll move on to assigning them using the AFE command. We'll select the zone for the first material, which will be the studs, by choosing the group that contains all of them. And so at this stage, we've just defined the zone for the studs and assigned their material. Once we close that, you'll see the info panel on the left showing the full AFE command. In that command, the first zone sets everything to the valve material. Then the second line assigns the stud material specifically to the stud groups. So first the whole mesh is a valve material, and then we override the studs with their own material. Now the next step is to handle a multiplication function that we will use as a ramp for the load. We'll create this with the diffie function command. Define a variable called display and assign it a value. So now I'm going back to the part where we define variables for the calculation. First, I'm creating a variable called tightening, which is the pretension value I apply to the bolt. This tightening variable will control all the variables. The first one depending on it is the display that I just created. The second one is react, which is the reaction force, which I will use in the calculation as well. Next, I will define a fluid pressure variable, pFluid, and give it a value directly that is not linked to tightening. I'll also create pFond variable for the bottom pressure and give it a value Finally, I'll define P opère for the cover pressure and a variable PF0, which is simply P opère plus P fond. Now I'll go back to my defi function command and rename it F0. After that, I will copy paste it and create a second function for the reaction force, which is F1. I will do the same thing, create the same multiplication functions for both pressures, which are the fluid pressure and the PF0. Now we are moving to the next step, which is about the boundary conditions and the loads. Since the constraints and contact conditions are already set up, now we just add the load definitions. We'll use Salome-Meca F to apply the loads as functions like the F1, F2, and 3 we have created, rather than just scalar values. I click on press rep because I want to apply a pressure load. I select the relevant groups, which are hat press and body press, and under the press keyword I will choose F2. I'll do the same thing for the groups that are body seal and hat seal, assigning them the F1 loading. So now I will add another loading, which is face force, using the Salome-Meca F. I'll select the FZ component and choose F3 function that we created. Then I'll assign it to the group called hat top. So the final step for the load-in part is to create a rigid link between the hole in the body and the rest of the body to stiffen that area. We do this using liaison solide under Salome-Meca, and that's how we handle it. Alright, let's switch gears and move on to the analysis. We are going into a static nonlinear analysis. The solver is already set up. We'll just add the KLM to handle the element characteristics of our studs, which are beams. Then we'll include all the loads we defined earlier, which are F1, F2, and F3. By doing that, we simply click on OK to confirm the command and move on to the post-processing commands. As an output, I will need the sigma-Elga, which is the stress at the ghost points, and the von Mises stress for the whole mesh. I'll request these using the calc_champ command. Now we need to create a NumPy table that will contain our output, the maximum von Mises stress. To do this, we use the creatable command and specify the output field we want to extract. After that, I'll use the calc_tab command in order to compute the maximum absolute value of the von Mises stress. Then we export this table using Improtable, making sure to select the NumPy table format because this is the format that Perselis can read. Once this is done, we move on to the History tab where we prepare the parametric study. In the parametric section, we can explore all the available variables and select the ones that are relevant for our study. When we're ready, we click on Go to Perselis to switch to the Perselis interface. Here we can see the main window displaying all the variables along with their default values. By clicking on Edit, we can view the script that Perselis will execute. It is recommended to save this. It is recommended to save this script manually because Salome-Meca does not save it automatically. We can also modify it if we want to customize the flow even further. Finally, we click on Evaluate to run the full computation chain using the default data set. From here, we can take advantage of Perselis's capabilities, such as design of experiments, sensitivity analysis, surrogate modeling, uncertainty propagation, and more. And this brings us down to the end of our video. See you on the next one.